Hello everyone, this is Ashish Agarwal. My topic for the term paper and for this presentation is the effect of parallelism on sorting and searching algorithms. So let's dive in. The agenda of the presentation is as follows. First, we'll go through the overview and we'll also discuss the idea of parallelism. Next, we will see some previous works on sorting and searching parallelism. Next comes the more important part where we will look into some case studies where some great minds use different ways to achieve parallelism in terms of sorting and searching. This section is further divided into three subsections. First, we see how parallelism on such algorithms is achieved by leveraging graphical processing units or GPUs. Then we see how it is achieved using multi-core central processing units. And finally, we go into shared memory. Next, we will talk about some other contributions that were quite noteworthy in this field. And of course, it shouldn't be missed. Finally, we talked about the conclusion and future scope. Let's start with the overview. So, why do we need parallelism? Instead of increasing the computational power of individual processor, what we can do is we can make multiple processors work in unison to complete the tasks. Next, what is sorting? Sorting refers to the process of arranging elements of a collection, or more popularly an array, like what we use in most languages, in a particular defined order. The defined order can be ascending or descending. Ascending basically refers to the arrangement from the least to the largest, while descending refers to the arrangement from the largest to the least. Next, what is searching? Searching is again what we say in terms of a collection or an array. It refers to the process of finding a particular element within an array or a collection. So, what's the basic idea of parallelism? Basically, before diving in, we can first get the idea of how parallelism works. So, what we do is we break a large problem into several subproblems and let individual processors work on each subproblems. Finally, we combine all the work of individual processors into a final answer. What is the result that we get? Basically, this process reduces the computational time by several folds. However, the amount of time that gets shortened depends on the effectiveness of the algorithm. Let's talk about a first case study where we discuss how algorithms of interest are optimized for parallel processing by leveraging graphical processing units. There are lots of interesting works in this topic. However, what we're gonna do is we'll discuss two among the most noteworthy ones. First, we look into a hybrid approach. This technique partitions data and uses multiple graphical processing units of threads to parallelly perform a Bytonic sort. It then recursively applies quicksort to the generated partitions. It is proven that this approach gives much better performance than the traditional quicksort algorithm. Second, we look into a Bytonic merge sort technique. This technique takes advantage of many cores of GPUs and shared memory for optimizations. The input data is partitioned and sorted using merge sort. Finally, the partitions are merged using a merge sort variant that is optimized for GPUs. Apart from the techniques that we just saw, there are various studies that mostly compares different algorithms and focuses on general optimizations. Some of them are memory coalescing, thread coalescing, and loop unrolling. So what is coalescing and loop unrolling? Coalescing is basically a technique in which adjacent blocks of free memory or free threads are merged together. Loop unrolling is a technique to optimize a program's execution speed at the expense of its binary size. For our next case study, we see how we can take advantage of multi-core central processing units for effective parallelism for sorting and searching. Once again, we see two techniques of interest to get a general idea of the approaches taken to leverage multi-core CPUs. The first approach combines parallel quicksort algorithm and the parallel merge sort algorithm. Once again, the input is broken down into multiple partitions. These partitions are sorted using the parallel quicksort technique, and then the sorted partitions are merged together. A parallel binary search is applied to the sorted set. Although this technique might seem trivial, it is quite difficult to implement in terms of parallel processing. It uses OpenMP, which is a shared memory multiprocessing programming interface. Speed increase is directly related to the increase in the number of cores, although the ideal number of cores varies a lot from system to system. Second, we have a two-phase technique where it starts by choosing a pivot element at random. The data is partitioned into sets that are larger and sets that are smaller than the pivot element. This step is performed recursively and a quicksort technique is applied to the partitions. Finally, the partitions are merged in parallel using the multi-core CPUs. It must be noted that the partitioning and merging steps are strictly performed on separate cores. Like the combination technique we just discussed above, this technique too uses OpenMP for effective parallel processing. Next, we'll look into a third case study where we see how we can leverage shared memory systems for sorting and searching optimizations. We'll discuss three different types of algorithms. First, let's talk about the adaptive Pythonic sort. So we've talked about Pythonic sort quite a lot in our previous slides. It is a pretty cool algorithm when it comes to parallel processing. Now we'll discuss about a modified and optimized version of Pythonic sort called the adaptive Pythonic sort. Why is it called an adaptive Pythonic sort? Well, it adapts to the input data, or rather the size of the input data and the number of processors. How are these optimizations done? Basically, the authors use shared memory systems to achieve the desired performance and the adaptability of the algorithm. It has been shown that this algorithm is pretty effective for large data sets. So next we have a parallel radix sort algorithm. What is radix sort? So radix sort is basically a sorting technique that sorts data based on a group of digits that share the same value. The parallel radix sort uses shared memory to improve the sorting efficiency. This parallel technique is divided into three phases: the partitioning phase, the sorting phase, and the merging phase. Each phase can be performed independently and hence can be performed in parallel. Finally, we have a parallel selection sort algorithm. In the selection sort algorithm, the smallest element is picked from the unsorted part of the collection or an array and moved to the beginning of the sorted collection. In a parallel selection sort algorithm, the picking up of this element, or what we call as the selection phase, involves the use of binary search. Moreover, this algorithm uses shared graphical processing units to achieve such high performance technique. Since this algorithm uses a divide and conquer technique, the steps can be performed in parallel. Our next topic of discussion is related to some other works that have had a significant impact towards parallelization of sorting and searching techniques. We discuss four such works. Let's start with the first one. There was an algorithm proposed by the authors Dong and Wang where they used field programmable gate arrays, or FPGAs as you see in the slides, to design a parallel technique. Field programmable gate arrays are integrated circuits that can be reprogrammed for custom use. These circuits provide flexibility and the ability to perform parallel tasks very efficiently. The proposed algorithm uses radix sort as it involves multiple pipeline stages. So these pipeline stages are timed to ensure efficient data processing and optimization to minimize the use of FPGA resources. The design and implementation of this work is described in terms of VHSIC, hardware description language, or as we call it, VHDL. Next, we have a parallel merge sort algorithm. So what is merge sort? Merge sort is a popular sorting algorithm, as we all know. So which recursively divides a collection into two halves, sorts, and finally merges both the halves. It has a worst case time complexity of O of n log n, which is pretty good. Although the parallel version of the merge sort algorithm optimizes the performance even further by performing the sorting step of the recursive halves in parallel. The authors of the parallel merge sort technique discuss two implementation strategies. First, using shared memory, and second, using distributed memory architectures. With the shared memory implementation, OpenMP directors are used to parallelize the algorithm across multiple threads. With the distributed memory implementation, a message passing interface or MPI is used to parallelize the algorithm across various nodes in a cluster. Next, we discuss a vector-based parallel algorithm that is specific to integer sorting for shared memory parallel computers. Let's first talk about what is vector processing. Unlike the traditional scalar processing, vector processing involves the processing of multiple data elements simultaneously using a single instruction. Like many other algorithms, this technique also involves the use of radix sort to first divide the input into smaller chunks. The interesting part, however, is the merge phase, where the chunks are merged using a vector-based merge technique. The authors of this work discuss the implementation with respect to a shared memory parallel computer called the Fujitsu VPP 500. At last, we have a partitioning and sampling technique. Again, like we've previously seen, this algorithm too divides the input into multiple smaller partitions. However, the partitioning is done using a sampling technique. This sampling technique selects a small subset of elements from the input data, which is then used to define the boundaries of equally sized intervals between the partitions. Next, what this algorithm does is it randomly selects a fixed number of samples and sorts these samples in parallel. The sampling technique that we just discussed is used to define partition boundaries, which reduces the communication overhead among different processes and the amount of memory used for sorting. We've discussed a lot related to sorting and searching parallel processing. So now let us sum it all up. We first went through some definitions that is important to understand the topic. Then we talked about the idea of parallelism. We also discussed how performance in sorting and searching algorithms is important. We then looked into several use cases illustrating past works that take advantage of graphical processing units, central processing units, and shared memory systems. We then went into discussing other noteworthy contributions like the use of field programmable gate arrays, parallel merge sort, vector-based parallelism, and partitioning and sampling technique. Now we come to the conclusion. We can now say that parallel processing plays a significant role in the effectiveness of computation, and its use is likely to grow in the coming years. Sorting and searching algorithms are already impacted by parallelism and are already considerably used. As the number of cores continue to increase and the popularity of GPUs continue to rise, the complexity of parallel processing will continue to increase along with the advantages. For a final slide, let's discuss the future scope of parallel processing on sorting and searching. The future of such algorithms could involve investigating the impact of data distribution, such as partitioning, replication, and skew. Moreover, communication overhead is still a problem in most of these techniques, which can also be reduced in the future. Finally, new hybrid approaches can rise up, which could lead to even better performance improvements. That's all I had. Thank you for your time.